Hello everyone. Today we're going to talk about graph coloring problem and see that how we can solve this problem using backtracking. In the previous video we talked about solving the n-queen's problem using backtracking. So here we have a graph or like a map that has four regions. Okay, and we're going to color these regions with three colors that we have: the red, blue, and green, such that none of the regions that are neighbors to each other have the same color. Okay, so assume that you are putting red for region 1. Okay, so red for region 1, so it means that none of the regions 4, 2, and 3 can have the color red. Okay, so let's say that we have color red for 1, then we, let's say, have the color blue for number 4. Okay, it means that now color number 3 cannot have the blue or red. Okay, number 2, region number 2 still can have the blue because 2 is not a neighbor of 4. So the only color remain for 3 is green, so it's gonna be green. Okay, and now as you see, the only the only color that is remain for 2 is blue, because its neighbors 1 and 3 both have colors red and green, so it cannot have these things, so it can have only color blue. Okay, so that's one example of the graph coloring, okay, or the map coloring. So why we're calling it graph coloring? We can show this region or this map using a graph. Okay, so let's say that we have this vertex or node 1, then we have this node 2 here, 3 and 4, and as you see here, 1 is connected to all other nodes. So 1 is connected to 2, 4, and 3. Node number 3 is also connected to all other nodes. Okay, 2, 3, and 1 and 4. Number 2 is connected only to 2, 3, and 1, and number 4 is also connected to number 3. So here 1 was red. Okay, so I'm gonna just have this one red. Okay, so red, and 2 and 4 were blue. Okay, and number 3 was green. And as you see, none of the neighbors have the same color. 4 and 2 both have color blue, but they are not neighbors of each other, so that's fine. Okay, so that's one example of the graph coloring problem or map coloring problem with having m colors. Here m is equal to 3. That means that we have that is 3 colors: red, blue, and green. Okay, so now we're going to see that how we can solve this problem using a backtracking approach. Okay, so assume that you're choosing the color red for the first one, for the first node, and then you have the, let's say you're choosing also the color blue for the third one. So you may say that, okay, now I'm gonna choose number like the color red again for node 2. Okay, but 2 is the neighbor of 1. Okay, 2 is the neighbor of 1. It cannot have the color red. Okay, so you're backtrack to the number 3, and maybe you're choosing another color, or you're back to number 2 and choose another color. Okay, so that's how we are can approach this problem using a backtracking way. So the algorithm for like the m coloring problem, like using a backtracking, is similar to what we have for the n-queen's problem. The only difference is that the promising function is different. Okay, so the structure is really similar, but the promising function is different. Also, we have some small changes in the main function that solves the problem. Okay, so I'm going to show you the procedure or the function of uh, the graph coloring problem. Okay, so that's the procedure for M coloring problem or graph coloring problem. So similar to N queens, first we're checking like if it's the node with the color associated with that is promising. If this is promising and I that here is the node, the number that is associated with any node is equal to n, that is the number of nodes that we have, then we are printing the like the array of colors that we have associated with each node. Otherwise, for every color that we have that is from 1 to m, okay, so here in the example that I provided, it was m equal to 3, red, blue, and green. Okay, so for every color test, that if you can assign that color to the next node, so I is, let's say that's the first node, then you're saying that for every color that you have, see if you can assign that color to the array that we have, we are storing for colors, and then call the function again. Okay, so that's the recursive function, and it's doing the depth first approach or the preordering on the tree that it creates. Okay, as I said before, we are not actually creating a tree, but it's resembling a tree because it's a recursive function and it's like goes through the steady space tree. And a promising function in the M coloring problem is a little bit different, because the conditions and the condition we need to check is different. So here we still have we have here the column, the index j. That j is all the indexes that are or all the nodes that we have visited before the current node I. Okay, so let's say that I have colored all the nodes 1, 2, and 3, and now is equal to 4. It means that now I need to check that if the color of node 4 is compatible with the colors of the 3 previous nodes. So that's why we have while j is less than I, when we are increasing j every time. So we are checking with all previous nodes before. And then if the color are same, okay, so we said that if the color are same, and we also need to check that if they are neighbors. And this W says that if the weight of I and j is equal to 1. So if this is we have a JC matrix of a graph, okay, so as we learned before, if this is equal to 1 means that they are neighbors of each other, or there is a direct edge between these two nodes, I and j. If this is equal to 0, it means that there is no edge between nodes I and j. Okay, so if there is an edge between I and j, and also the color are same, okay, then it's promising false. Otherwise, if they are not neighbors, okay, or the color is different, we're not changing the promise, and the promise is promising still true. So for every node, node and which each color with its color, we are checking that. Okay, so that's what happens for the M coloring problem. So, and if you want to like to see that how many nodes we have in the steady space tree, okay, I'm gonna like show the tree, but let's just see the formula here, and then we'll go back to the tree. So at first we have the empty tree. So at first we don't have any nodes colored. Okay, so we have only one node. Then in the next one we have M colors. So let's say that the first node has 3 M options to be colored. Okay, so we have M. The next node will be like the next level will be M to the power 2. Okay, because again every, like let's say now it's like node 2, and node 2 based on the what it has on previous level, okay, it can have M colors. Okay, so for every we have M nodes above and now M nodes here, so together it's gonna be M squared, and so on until we have the N nodes, so it's gonna be M to the power N, that is the number of leaves that we have, and together that's gonna be the number of nodes in our state space tree. Okay, as I said, I will show you the tree so you can have a better understanding of this formula here. So now we have this tree. So at the first level, we root, we have only one node. So we have the empty, like the graph without any color. On the next level, we have three nodes. Okay, the first node with color red, the first node with color green, or the first node with color blue. Okay, so we have m nodes at level 2. Then on the next level, okay, for every other one, so for example, for one in red, okay, so that you can color the second one red or green or blue. Also, when the first one is green, so you can have second one again red, green, or blue. Okay, and also when it's the first one is blue, you can have also the other three ones. So together, gonna be m to the power 2, and totally the number of nodes in your tree will be 1 plus m squared plus m cubed, so on, plus m to the power n, and n is the number of nodes that you have in the tree. Okay, and m to the n itself is the number of leaves that you have in your tree. Okay, so one thing about the graph coloring problems and in backtracking problems in general is that backtracking like approach doesn't mean that it's always better than the brute force. Okay, although we are doing some optimization such as pruning, okay, when there's no way like to have a solution based on some values, okay, but it still might not be better than like the brute force that is finding all the solution. Okay, so assume that we have this graph here in our example, but we only have two colors. Okay, so let's say we don't have the color green anymore, and we just want to color this graph using two colors, red and blue. Okay, as you see, there is no way that we can accomplish this task, and there is no solution to this problem. Okay, but the backtracking problem like approach doesn't know this that there is no solution for that, so it needs to like go and exhaust all the like the tree space, like a space tree, to find that there is no solution for that. Okay, here for example, if you choose color red for node 1, okay, so, and if you choose color blue for number 2, okay, you are left with no color for node number 3, because either it can be red or blue, and but at the same time number 1 and number 2 have the color red and blue, so you don't have any solution here. Okay, so but in general the backtracking like solution or a backtracking algorithm works well in many cases. Okay, so again, backtracking doesn't mean that it's gonna be for all cases and all the time, but it means that for most of the cases, for many cases, backtracking approach is a good way to solve the problem. So that's for like graph coloring problem and solving it with the backtracking approach.